Okay, so this is an extremely basic introduction to gas laws. Prior to now, most of our reactions, have been taking place in aqueous form, liquid form, where we have ions dissociating and then mixing back together to create something new. But that's not always the case. Sometimes we'll have gases interact with one another. But gases kind of follow their own rules when it comes to their behavior. Solids, typically speaking, they're stuck, particles are really, really close together, not a whole lot of motion, set shape, set volume, can't wiggle too much. Next step up, liquids, higher temperature, higher amount of kinetic energy. We can move a little bit more, but not that much, so we have a fixed volume, but not a fixed shape. Once we move on to gases, now all bets are off. Those particles are just moving all over creation, crazy kinds of motion, all kinds of nonsense. So there's a couple of just truths that need to be stated about gas nature before we move a whole lot further. Hopefully you can read that. There we go. It's a little better. So the first thing is that gases do in fact have mass. The particles are assumed to be too small themselves to actually matter, but at the same time they do actually have a mass. This would allow us to calculate the amount of moles of a particular gas. In fact, that's usually the preference whenever we're calculating, is that it's always done in a mole. Unlike solids and most liquids, gases can be compressed. We can squish them into smaller volumes. Another difference between gases and the other phases is the fact that gases fill the entire container. So this means that whenever you have a problem that says that the gas is in a 7-liter container, the gas actually takes up 7 liters. That is, in fact, the volume. So you don't have to have like the exact size that the gas particles themselves take up. They will disperse and diffuse throughout the entire space. Gases can move through each other. This is called diffusion, when one gas moves through another. Gases also exert pressure. When particles bang up against the walls of whatever is containing the gas, we call that pressure. And that pressure depends on your temperature. So temperature is a measure of kinetic energy in a substance. The more kinetic energy it has, the more those particles move around. The more they move around, the more likely they are to run into the walls of that container. Now, all of these particulars of gas behavior are summed up. Let me move my camera here. Oop, wrong way. Are summed up in this thing called the kinetic molecular theory of gases. This is kind of like Dalton's law for atoms, same principle. We've got several particulars here about gases. So, as previously discussed, I should mention, a lot of times you'll see it abbreviated KMT, because that's a lot of words. Anyway, gases consist of tiny particles or atoms. Well, duh. Next bullet. These particles are so small that compared to the distance between them, the volume of the individual particle is negligible. So this means when we're talking about the volume of the gas, you don't have to worry about how big the particles are. It's just kind of all lumped together into one thing. Since in gases the particles are so far apart, it's that distance between them that actually takes up the volume of the gas, as opposed to the volume of the individual particle. Moving on. Those particles are in constant random motion, so non-stop. Think small child on sugar. Just bouncing around everywhere, monkeys hanging from the ceiling, and they collide with the walls of the container. This creates pressure. So again, whenever those particles crash into the walls, think Newton's third law. Every action has an equal and opposite reaction. So particle exerts a force on the wall of the container, wall of the container exerts a force back. This is your pressure. But to make our life simple, we assume that the particles do not interact with each other. So while they do smack into the walls of our container, they do not smack into each other. This is an ideal principle. They do run into each other periodically in real life, but for an introductory chemistry class, it's just not necessary to take those small interactions into account. We won't even be talking about the real gas law in this series of videos. So we are making our lives simple as possible, ideal scenarios, please. And the last bullet is just kind of a reminder. The average kinetic energy of our gas is directly proportional to the temperature, because again, temperature is the average kinetic energy of anything. All right, moving onwards. See if I can get through all of these notes before my camera time runs out. Measuring gases, couple of things you need to know. Measuring the amount of a gas, as previously stated, it must be moles. Moles is usually represented by the letter N in these problems, and so you convert to moles however necessary. Typically, you'll be given them in grams, so it's just formula mass, off you go. Volume, represented by the letter V in equations, is usually measured in liters. We can use some other units, which we'll talk about in a second, but typically you'll see liters. The temperature is the big one, because this is no compromises, do not pass go, do not collect $200. Temperature must be in Kelvin. The reason for that is that the Kelvin scale does not go into negatives. As previously discussed, temperature is an average kinetic energy. Can't have negative energy, so why would you have negative temperatures? It just doesn't make sense. The bottom of the Kelvin scale is called absolute zero, where there is absolutely no motion, no energy, no nothing. So your gas law problems, your temperature must be in Kelvin. Just make it a habit. As soon as you see a temperature, convert it to Kelvin. The conversion from Celsius to Kelvin is pretty simple. Just take your Celsius temperature, add 273, gives you Kelvin. Pressure, usually represented by a P, go figure, in these equations, and we got several different units that we can talk about. So, just to harp on those units a little bit more, amount. Did I mention always use moles? No ifs, ands, no buts, always moles. We like them. Use them. Volume, as previously stated, we can use liters. That's typically the unit that's used when we get to the the ideal gas law. You will have to use liters, but in the combined gas laws, anytime you have a change, your unit doesn't matter so long as you are consistent. So we can use centimeters cubed, milliliters, liters, millimeters cubed, kiloliters, doesn't matter. For your use and information, a centimeter cubed is the same volume as a milliliter, so this makes 1 liter equals 1,000 centimeters cubed. Useful information. Temperature. Did I mention the Kelvin? By the way, you must always use Kelvin. And in case I forgot, don't use Celsius. Pressure. Here it is. Force per unit area. Ladies, this is why when you wear high heels, your feet hurt so badly. Big force, little area. But in gas laws, again, it's how many particles strike the wall of a container per unit area. Our units include millimeters of mercury, so they're literally talking millimeters high of a mercury column supported by the atmosphere. Torr, or atmospheres. This is the most common, atmospheres. So 1 atmosphere is the same thing as 760 torr. 1 atmosphere is the same thing as 760 millimeters of mercury, so these two are almost interchangeable. It is the same thing as 1.013 times 10 to the 5th pascals. Sometimes you'll also see pounds per square inch, but these are the only units that I make my kiddos know. That atmospheric pressure, we are in fact talking about the pressure of the atmosphere around you. And the device that we use to measure that is called a barometer. You hear that on the weather. They talk about barometric pressure. So when barometric pressure is falling, yes, in fact, the pressure of the air around you is getting less. A low pressure system is in fact less pressure pushing down on you. The reverse by a high pressure system. It was invented by this monk, by this dude here, and this was the first barometer. It had this little dish of mercury at the bottom, and then a tube up top with a vacuum of air at the very, very top allowed the mercury to move up and down. And so the legend has it that Torricelli was taking this little apparatus from his where he stayed up to his laboratory on the top of a high, high hill, and as he walked and the altitude changed, he noticed that the height of the mercury column also changed. Being a scientist, he had to repeat the experiment, dashed back down the hill, and to discover again that in fact the mercury column had changed. The air pressure pushing down on this mercury here was forcing it up the tube. So when we say millimeters of mercury, we literally mean millimeters of this mercury column. Today, more commonly, they look like this. A little bit smaller, a little bit more compact. So atmosphere, again, Here's our pressure units that we were talking about. There's that PSI, pounds per square inch. Just to give you a little bit of a point of reference, your tires usually have 28 to 32 pounds per square inch. 1 atmosphere of the air around you is only about 14.7. Let's see, how much more do I want to talk about? Alright, as far as background goes, one more thing I got to show you. Standard temperature and pressure, these are 2 typical abbreviations that you'll see in gas law problems. The first one, standard temperature and pressure, is STP. That's 273 Kelvin and 1 atmosphere, so that's 0 degrees Celsius. Normal temperature and pressure, NTP, this is room temp, so about 20 degrees Celsius and 1 atmosphere. You'll see those abbreviations a lot in problems. Alright, the next video we will introduce the first of our sets of equations dealing with changing situations. Check it out.